Hello friends, my name is Chinmay Deshpande. In this video lecture, we are going to discuss about a numerical on equal area criteria. Consider a first numerical. The figure below shows a generator which is connected to a metropolitan system, that is nothing but an infinite bus, through a high voltage lines. Per unit reactances of generators, transformers and transmission lines are given in the figure. We have to find it out here, a critical clearing angle, that is delta CR, when the three-phase fault occurs at a point P. So this is the location or this is the position at which the fault will occur. Whenever the generator is delivering 1 per unit power, the voltage behind transient reactance is 1.2 per unit and the voltage of the infinite bus is nothing but 1 per unit. So let's solve it step by step. Before that, first we will write all the given things. So I will enlist all the given things. First one is nothing but internal voltage of the generator. That is, we have given this E dash value which is equal to 1.2 per unit, which will be internal voltage of the generator. Then voltage of the infinite bus bar, that is mod V, we can write it as 1 at an angle 0 or 1 per unit. Then here the transient reactance of the machine, here it is given J0.3. So I will write it here J0.3. This is your transient reactance of the machine. I can write this is XD dash, which is in per unit. Then the line reactances has been given, that is I can write now X1 is the first line whose reactance is J0.25 and X2 is the second line whose reactance is same, that is J0.25 each. Now here the transformer reactances have also been given. The transformer reactances I can represent these as XT1 will be equal to XTT2 will be equal to XT3 will be equal to XT4, because all the four transformer has the same reactance in per unit, which is J0.15 per unit. Then this J0.15, this is nothing but what? I will write it as infinite bus reactance. So I will represent this as Xi, which is equal to J0.15 per unit. And again it is mentioned, the generator is delivering 1 per unit power. What is the meaning of that? Generator delivering is nothing but we have given this value as a PE, or I can write it as PE1. So what it includes or what it indicates, it is electrical output of the machine, which is to be given as 1 per unit. Now it is clearly mentioned in the numerical, the fault will be at point P, which is three-phase fault. So now we will do stepwise. First one I will write it as case A. Case A is nothing but pre-fault condition, or in other words you can write as before the fault condition. Now if you see this diagram, before fault what happens? These two lines are exactly parallel with each other. So if you want to find it out effective reactance, then how I can write? I will write here a formula for finding out effective reactance or reactance during pre-fault condition, which is represented as suppose X1. So here XD dash is there, which is shown here XD dash. Then these two are parallel. So you know A parallel with B. How you can write? A into B upon A plus B. So I can write it here. First one is nothing but XT1 plus X1 plus XT2. Okay, so this will be XT1, this is your XT1, this will be your XT2, this will be your X1. Similarly, this is XT3, this is X2, this will be your, let's say, XT4 reactance into A into B. Into means what? XT3 plus X2 plus XT4 divided by what it will be? It will be like this: XT1 plus X1 plus XT2 plus XT3 plus X2 plus XT4. So up to this we have written this. This is your xd dash. These two are parallel, and to this combination, this xi is in series. Xi is connected in series. So how I can write here? Plus I can write it as xi. So if you substitute all the values, now I am not going to write all the values. You can do it on your own. Xd dash is 0.3, xt1 is 0.15, x1 is 0.25. This xt2 will be 0.15. Okay, then this xi will be equal to 0.15. The given values, if you substitute, then you will be able to find it out by using your calculator. X1 will be equal to J 0.725 per unit. This will be what? J 0.725 per unit. What is this? This is your, you can say X is the reactance. So I can write it as, this is your pre-fault reactance. This will be pre-fault reactance. So this is the first case when we have taken here as a pre-fault condition. Now we will take a second case, case B. What happens during case B? Case B is nothing but whenever there is a fault, or I can write it here as during fault at point P. Now what I will do, whatever diagram we have, whatever this diagram we have, to calculate the transfer reactance during fault situation in between generator and the infinite bus, we have to reduce the network, and then we have to find it out here value of x2. x2 is nothing but reactance during fault situation. So how I can reduce this? Let me draw this diagram from the diagram which is given above. So there is a one generator, we can say this is E dash, which is equal to 1.2 sorry, 1.2 per unit. Then here there will be a reactance which is J.3 xd dash. Then after that, if you see, this has been covered. Now there are two branches, so I will do this for these are the two branches. First one is nothing but what? This one will be J 0.15, which is xt1. Second one is nothing but J 0.25, which is x1. Okay, then this will be J 0.15, which is xt2. Now here you will get J 0.15, which is xt3, and as the fault is occurred here at point P, so therefore what I will do, I have to mark it here point P. So I will mark this as a point P. Here if you see, again the line portion is there, x2. Again here the reactance of the next is nothing but J 0.50. So I will complete this. After that, if you see, we have a value of xi. What is that value of xi? It is J 0.50. And here now you will have 1 per unit, which is nothing but V. And I am going to connect this. I am going to connect this. So this will be your reactance diagram, and it should be connected here. Why? Because the fault is there. Now what I will do, I will make these reactances, I will add these reactances because it is in series. I will add these two also because it is in series. Okay, so I will modify, or I will redraw this diagram again. So after redrawing the diagram, what you will get, this is nothing but your J 0.3. Here this will be E dash equal to 1.2 per unit. So let me open this, just a minute. Let me draw this. Then next is nothing but what you observe, all these are in series. So 0.15 plus 0.15 plus 0.25, how much it comes out to be? It comes out to be J 0.55 per unit. Then it will be as it is, that is J 0.15. This will be the point P. Okay, I will represent this point, let's say for a simplicity, I will represent this point as a A. This is P, and I will say this point is nothing but you are supposed B. Now here again 0.25 plus 0.15. So what you will get? It is nothing but J 0.4. Then here again you have to draw this xi, which is equal to j.50, and let me complete this infinite bus voltage 1 per unit. So this will be your diagram. This will be a total diagram. Now I'll take another color because it will be easy for me to show the few parameters or show a few things. Let me take the color. Okay, I'll take this green color for the sake of simplicity. Now here if you see, now what I will do, I will convert here. Now here we have to convert first delta to star, and then we have to convert star to delta. So again I will represent this as a A, this is P as it is, this will be your B. So how you can represent it? You know that you can represent it like this. Okay, converting your delta to star. So there will be one reactor here, there will be one reactor here, and one reactor here in between. So how we can write? Let's say this point which is shown here is nothing but O. This point is O. Let's see. So therefore converting this total delta assembly delta to star. So what happens if we convert this delta to star? What you will get here? You will get it as, I will write it here, XOA. OA means what? This. So how to find it out? XOA? Opposite multiplication divided by sum of all. So opposite multiplication means what? J into 0.15. Now don't take here J, or you can take J as a common here. 0.15, okay, into 0.55 divided by sum of all, that is 0.15 plus 0.55 plus 0.4. So if you solve this on the calci, you will get answer at J 0.075 per unit. So this will be the answer. This is for XOA. Now similarly, can I find it out XOB? Yes, we can find it out. How to find it out XOB? Here, opposite, what is opposite? J 0.4 and 0.55. So I will write it here. J 0.4 into 0.55 whole divided by sum of all, 0.15 plus 0.55 plus 0.4, which will be equal to what? J 0.2 per unit. You can solve it by taking calculator. And how to find it out? XOP. Now what are the opposite things? 0.15 and 0.4. So therefore I will write it here as XOP will be equal to J 0.4 into 0.15 whole divided by 0.15 plus 0.55 plus 0.4, sum of all the reactances. So if you find it out, you will get here answer as J 0.0545 per unit. I think you understood this, what we did. First we converted this delta into star. Now I will redraw this diagram. How to redraw this diagram? So first thing will be as it is. This will be as it is, your reactance, that is J 0.3. Then here you will have E dash equal to 1.2 per unit. Now what it will be here? Now instead of drawing this, we have to draw whatever things in a green color. So how we can draw this? This will be your point A as it is. Then there will be one reactance. Again here there will be one reactance. Again there will be here one reactance. Okay, this is also one reactance. Here is connected here. So this is your 1 per unit. This will be your XI, which will be J 0.15. This is your point O. This will be your point B, let's say, and this will be your point P, suppose. Okay. So what is OA? XOA 0.075. So I will write it here J 0.075. XOB, how much that value? J 0.2. So I will write it here, and this will be J 0.0545. So what we did here, basically we converted whatever this delta first into a star. So we will get this circuit. Now can I add these two, because these two are in a series and these two will be are in series. So how I can draw this circuit again? Let me draw this. So it will be, this is your one reactance, another reactance, this will be your third reactance. Now here I can draw it like this. So this is 1 per unit. This E dash will be 1.2 per unit. If you add these two, then what you will get? J 0.375. Is it? Yes, J 0.375. This is J 0.0545. This will be J 0.2 plus 0.15 means what? It will be 0.35. So I will keep this name as O only. This will be your P only. This is your B, and this will be your A. Now what I want to find it out? I want to find it out reactance during the fault. So therefore again I have to convert whatever this star into delta. So let me take again another color. I will take a red color here so that it will be easy to show it. So what I will do now, converting your star to the delta, and it is expected to find it out only a reactance between these two, because we want to find it out reactance during fault only. So you can represent this as a x2, you can represent this as a x2. So how to find it out? You know how to. Here I will write it here, convert star to delta. So what to do? What is opposite value here? What is the opposite of x2? J 0.0545. So it should be taken at the denominator. So I will write it here, formula. In a first year of engineering you have studied this, or in a diploma also you have studied this, how to convert star to delta. Okay, I will take here J common instead of taking J. Okay, now and how to write for the numerator? How you will write? First multiply with second, second multiply with third, third multiply with first. So it will be like this: 0.375 into 0.35 plus 0.35 into 0.0545 plus 0.375 into 0.0545. So if you solve this, you will get an answer for x2 in per unit. What will be the answer here? Once you find it out with the help of calci, then you will get this answer as 3.133 per unit. So what is this? This will be your reactance, but this is during fault reactance. So I can write it here. This will be your during fault reactance. During fault reactance. So this is the case number 2, that is during fault at point P. Now we have to write for case number 3. What will be the case number 3? Case 3 or case C will be post fault. Meaning of post fault is nothing but when your fault has been cleared. So what happens during the post fault condition? Now whenever the faulted line is open, the transfer reactance will be what? Now as here the fault is at this point, so this line will be open. So what will be the effective reactance? 0.3 in series with 0.15, in series with 0.25, in series with 0.15, in series with 0.50. So how I can write? Let me write here equation for x3. So x3 will be equal to what? You can write it as x dash d plus xt1 plus x1 plus xt2 plus xi. So put all the values. You know now what are the values of all these reactances. So if you put it here, all the values, you will get answer as J1 per unit. So what is the meaning of this x3? This x3 is nothing but it is reactance during post fault condition. It is reactance during post fault condition. Now we have determined all the values. We have determined what is your x1, x2, x3. So if the question is asked to draw a p delta curve for this case, can you able to draw it? Yes, it is very easy. I will draw it here. So this will be your, suppose this is your delta. Okay, this will be your p. So I will represent it with different color. Let me try this. This is nothing but what? Let's say, let me draw it properly. This is denoted as PE1. PE1 means what? It is electrical output power. 1 indicates pre-fault or before fault, and its corresponding maximum power, it is denoted by Pmax1. How to find it out Pmax1? That you know. It is EV upon X1. It will be what? EV upon X1. Now in this step number 1, we forgot to find it out one important parameter. Once you got this Pmax1, can we find it out, once we find it out x1, can we find it out here Pmax1? Yes, we can find it out. How? This Pmax1 equal to E dash V upon x1 into sine delta. Okay. So Pmax, let me rub this. There will not be any term sine delta because Pmax1 equal to E dash V upon x1. So E dash, you know the term, what is a value? 1.2. So I will write it here 1.2. V is 1. Here you got this x1 as 0.725. So what will be your Pmax1? It comes out to be 1.6552 per unit. 1.6552 per unit. Okay. Then here if you see, if you observe, there was a one thing, I will write it here because it was missing from my side. So if you remember here, the given was PE1. PE1 was given 1 per unit. And initially, you know, initially your mechanical input PM0 will be equal to PE1. So what is PE1 and PM0? It is 1. How to find it out PE1? It is Pmax1 into sine delta, but corresponding value will be 0. Initially at point A, the delta will be equal to what? Delta 0. So how I can find it out value of delta 0? Please remember, while calculating or while solving such kind of numericals, keep your calculator in radian mode so that you will get answers in all answers in radian. So what you will get delta 0, how you will be find it out? Sine inverse of 1.0 divided by this Pmax1, which comes out to be 1.6552. So your answer for delta 0 here in radian is 0.6487. 0.6487. Don't forget to write a unit, it will be a radian. Okay, I forgot to tell about this step in the case 1, that is pre-fault condition. We have to solve it here only. Now if you go for a case B, also, here we can find it out Pmax2. How to find it out Pmax2? It will be equal to E dash V upon x2. So E dash is 1.2, V is 1 and x2 is 3.133 if you observe. So therefore, what is the answer of Pmax2? It comes out to be 0.383 per unit. So this is Pmax2. And definitely you can find it out Pmax3 also during this post-fault condition, which comes out to be what? Same formula, E dash V upon x3 will be there. So it is 1.2 into 1 upon 1. So which comes out to be 1.2 per unit. So these are the values of Pmax1, Pmax2 and Pmax3. So this is the first curve that I have drawn here. Let me show it to you. This is Pmax1. Now I will take another color for simplicity. Let me show this with this green color during fault. So let's say during fault is this. Okay, during fault is this. So I will take this dotted line. This will be your Pmax2, and this curve is nothing but what? This will be your PE2. PE2 is nothing but what? This is the maximum power transfer during fault situation. And let me draw the third one. Third one will be exactly in between these two. Exactly, it is in between these two. Now you will ask me, sir, why it is like this? You please check all the answers of Pmax1, Pmax2, PE1, PE2. You will definitely understood why the curve is like this. Let me first draw Pmax3. So I can say this will be your PE3. Let me draw here mechanical input. So I will draw here a mechanical input line. So it is drawn by this color. I will say this is nothing but your PM0 which was given here 1 per unit. So now if you take the curve or if you take the areas, then what will be the areas? What you will observe here, this is your point A where your PM0 and this curve is what? PE will intersect with each other. So I will take here a dotted line up to this. So this is your dotted line. Let's say it is delta 0 that you have find it out. Suppose your fault is clear at position this. Suppose this is your delta CR. So if you extend this, you will get this as a delta CR, and this one will be what? This one will be the maximum value, that is delta max. This is your pi. This will be 0. So let me show the regions where it will be. Let me show regions. Okay, I will take this color. So if you take this to this area, if you take this total area, then this total area, what it indicates? This total area is the accelerating area. And if you take this to this total area, then this area is nothing but deaccelerating area A. Now our aim is to find it out what is the value of cos delta CR. So we can directly use the formula because it is very easy. We can directly use. What is the formula of cos delta CR? Let me write here. Cos delta CR will be equal to Pn into bracket delta max. This will be delta max minus delta 0. This is a delta minus Pmax2 into bracket cos delta 0 and plus Pmax3 into cos of delta max. So this is your numerator and divided by Pmax3 minus Pmax2. So you have all the values with you. You know what is PM. You have determined delta 0. You have find it out by Pmax2, then Pmax3. But the thing is, we have to find it out here. What is delta max? We have to find it out here. What is the value of delta max? So how to find it out here? Value of a delta max. Please see now from the diagram. Here this is the point. This will be total pi. So from pi, what I want to do? I want to subtract some value of load angle delta in order to find it out this delta max. So please see it carefully. This line will intersect at this point, intersect to this PE3 at this point. Let's see. So here this delta value we have to take, we have to subtract, because see the distance from this to this and distance from this to this is same. Now the question is how to find it out this delta. How to find it out this delta? So let me tell you here. I'll find it out here. Delta max will be equal to pi minus sine inverse of, how I can write it? This will be Pn upon Pmax3. Pn upon Pmax3. How it is? See it carefully here. This line is your Pm. So I can say this is PM0. Okay. And this is the curve which is indicated by PE3. PE3 means what? It is Pmax3 into sine delta. So how to find it out this delta? Delta will be equal to sine inverse of Pm0 upon Pmax3. So you will get this answer, Pm0, or you can say Pm also, anyway. So if you subtract this value from the pi, then you will get answer for delta max. So put all the values. You know what is Pm? Pm equal to what? So I'll write it here, pi minus, again it should be in a radian, sine inverse of Pm is 1, Pmax3 we determined, it was 0.383. So if you solve this, you will get this answer as 2.1565. 2.1565. So now again you got this value for delta max. Substitute all the values here. Substitute all the values. So I will substitute here. Cos delta Cr will be equal to 1, which is nothing but your Pm into bracket 2.1565 minus 0.6487 minus 0.383 into cos of delta 0, 0.6487 plus Pmax 3, that is 1.2 into cos of delta max, that is 2.1565 whole divided by Pmax 3 minus Pmax 2. So it is 1.2 minus 0.383. So if you substitute carefully all the values in the calculator, you will get answer for delta Cr. So delta Cr comes out to be what? This is your critical clearing angle, 0.8499. This will be a delta Cr in radian. If you wish to convert it in degree, you can convert also it in degree. You know what is the formula or relation between radian and a degree. So in degree, if you wish to write, it is 48.69 degree. So this is what is the total problem for calculation of load angle delta Cr. So this is the one way, one method you can say, or one type of the problem in which you have to convert star to delta, delta to star, pre-fault, then during fault, post-fault, likewise, and you have to find it out here, critical clearing angle. There are two other methods also. Instead of converting this star to delta and a delta to star, the data might be given either directly in the form of Pmax 1, Pmax 2, Pmax 3, or data might be given either in the form of x1, x2, x3. Now, whatever conclusion that we have to draw, please see it carefully. I will write it here, all the values of x1, x2, x3, and all the values of, here let me write x1, x2 and x3, because this is very important, which is always used to ask for interviews or oral examinations. Now x1, what was the value of x1 you got? J.725. So I will write it here. X1 is nothing but what? X1 is J.725. This was the answer that you got once you find it out. Then what was the answer for x2? It was J 3.133. 3.133. Here if you see, third one, what was that? 1.0 per unit. So the question might be asked, what is the relationship between the reactances during fault, post-fault and pre-fault? So if you see x1, which one will be the, so I will write it here, x1, this x1 is 0.75, which will be lesser than your x3, that is 1 per unit, which will be lesser than x2. So please keep in mind this relation, this is very important. Similarly, if you go through this Pmax 1 value, what was the Pmax 1 value you got? It was 1.6552 per unit, J 1.6552 per unit. Pmax 2 value during fault, maximum power transfer was what? It was drastically reduced. It was 0.383 per unit. And if you take Pmax 3 value, Pmax 3, then it was what? J 1.2 per unit. So what was the relation you observed? So again, this is very important relation which might be asked for oral examinations. Pmax 1, okay, then Pmax 2 and Pmax 3. So I will write it here. Which one is the smaller? Yes, Pmax 2 is the smaller. Then Pmax 3 and then Pmax 1. So if you see your graph, you will see the same thing. Pmax 1, the first curve is of P1 whose maximum value is Pmax 1. So it is shown here. This is your Pmax 1. So this is your red color curve. Next is nothing but Pmax 3, which is in between. So if you see this Pmax 3 value, which is the value of this PE3, which is in between this first curve and the second curve. That is nothing but what? After clearance the fault. And this will be the curve which is of Pmax 2. Pmax 2 means during fault maximum power transfer. This will be the PE. So this is the relation which is very important. Please keep in mind these both relations. So this is what is about the problem solution of equal area criteria fault at a midpoint. If you have any doubt, please feel free to ask. Thank you. Thank you once again.